Lesson 3, Cocoa Collisions. This lesson really works to explore the why behind a scientific fact that many students instinctively know. Energy is spontaneously transferred out of hotter regions or objects and into colder ones. Translation: hot things cool over time to the temperature of their surrounding environment. We know that this is true for our pizza and for our coffee, but we rarely stop to think about why. Lesson 3 presents the students with the phenomena of a cooling cup of hot cocoa, and the Cocoa Collisions game is a model that helps students to answer the question of why this is happening by taking a look at what is happening at the molecular level. While this game has proved to be dynamic for students, it is important to point out the limitations that this model, like all models, has. When the cocoa is sitting at the table in room temperature, students slowly observe that it loses thermal energy and becomes the temperature of the surrounding environment. In this game, students use manipulatives and simplified calculations to show that this temperature is changed as a result of the transfer of thermal energy, and this transfer happens through the collision of molecules. Now we know that molecules are constantly moving. Air molecules, the molecules in the cocoa, and the molecules that make up the mug. All of them are moving. That constant movement results in inevitable collisions between molecules. And as those molecules repeatedly collide, there is a transfer of energy. Now, the first limitation of this model is that collective movement is not considered. You'll notice that students do not address the molecules that are hitting the side of the mug or the molecules that are colliding with other like molecules. There's two reasons for this. First, we don't address the collisions of like molecules. Initially, because the overall thermal energy of those molecules is similar, those collisions don't result in a noticeable change in temperature. Some molecules gain a little energy in a collision, some lose a little, and some remain the same, but the overall energy of that system, and consequently the temperature, is consistent. We call this dynamic equilibrium. Because we're focusing on what happens that does result in the change of temperature, these collisions are omitted to simplify the game. Secondly, we don't address any energy loss to the mug and how the mug may act as an insulator. Again, the goal of this game is very specific. In this game, the collisions that are addressed are those between the cocoa and the air that is directly above the mug. This game asks students to consider what is happening at the molecular level. The difference between the air and the cocoa molecules is that they don't have the average same thermal energy. On average, each cocoa molecule has more thermal energy than each air molecule. In this game, this energy is represented by an arbitrary set of numbers. You'll see those numbers here. So we have our cocoa molecules and our air molecules. Again, you'll see the limitations even in this visual model, but you get the idea. As those cocoa molecules collide with the air, there is an energy transfer, and things don't stay the same anymore. Because there is a difference in the average thermal energy between these types of molecules, the repeated collisions between the cocoa, which has more energy, and the air, which has less, result in the cocoa molecules losing thermal energy to the surrounding air. So repeated collisions mean that statistically, the cocoa is losing thermal energy through each collision with the air. In this game, over time, those repeated collisions result in a loss of thermal energy that can be measured as a change in temperature. Our hot cocoa is cooling. That brings up another important limitation of the game, this concept of a collision zone. Now, for the purposes of the game, the molecules that are colliding with one another are moved into a space that we do call the collision zone, and it can lead to a misconception that all thermal energy is only transferred through this delicate line where cocoa and air meet. The truth is a little bit more complicated. Remember, the like molecules are also moving and colliding, and the energy lost to the surrounding air means an overall decrease in the total energy of that system. So as the cocoa molecules collide and redistribute their energy, think that dynamic equilibrium again, the average energy of each molecule decreases slowly. We're able to feel and measure the evidence of this overall decrease as a decrease in temperature. So as you play this game with your students, keep in mind the intention and the goal of this game. It does a great job of modeling the exchange of energy through collisions, but like all models, it does have its limitations to consider.